the last talk of today. Oh my goodness, and of the whole conference. So I have the last person to introduce today. He's going to talk about ranking tennis players with Bayesian modeling. I am very intrigued by this, so let's welcome to the stage Francesco Bruzzesi.
Thank you. Right. Good morning, everyone. Thank you for attending. I want to talk about how we can use Bayesian inference to challenge the status quo of tennis systems, why this talk even exists. So I'm a data scientist, and I play tennis competitively for 12 years as a kid. I still follow a lot the tennis world and what happens. So I had a spare weekend, and I thought it was a fun time to spend when it's raining in Berlin. So that's how it started. So topic agenda of the day. I'm the last guy standing between you and enjoying the beautiful day in Amsterdam. So let's get to work. We'll start about what's happening with the current system and what's wrong with that, if anything is wrong with that. Then there is a Bradley Terry model that also some other speaker spoke about during the event. And finally, we get our hands dirty implementing that in PyMC. So hopefully, you learn about some tricks and tips about that. Then we finally do ranking, and we'll compare how these systems work. And finally, some other application and extension that one can reason about. OK, by show of hands, how many of you know how tennis system, ranking system works? Not many people. So let's start from that. It's a very simple system. It's point-based. Every week, there is a tournament. Players randomly match with each other, kind of randomly, given by the ranking. And who wins, go to the next round. When you lose, depending on the round you got some points. And at the end of the week, the points updates and the ranking updates, and those points are then used for the next week. And these points are kept for 52 weeks. So it's a year-rolling system. So is it bad? Maybe. OK, so we can say that it has a few flaws. So it's round-based. So depending when you lose, you get the points. It's not opponent-based. And for example, chess, you have Elo ratings, and it's opponent-based. So if you beat world number 1 in the first round, you will get more points than beating world number 100 or something. Here's not the case. And you can see these are the points awarded in Wimbledon. So depending on where you get, then you get some points. And that's it. It also can be a number game. Since the points sum with what you have, here there's an example of two players that it's rank number 4 and rank number 8. And the win rate is better for rank number 8, but he played less matches due to injuries, and so it's as a lower ranking. Surfaces are interchangeable. So the points that you get in one surface are used basically for everything, and it doesn't matter which tournament is going to happen next week. And this is bad in a way, because there are some surface specialists that like a lot playing some surface, but they don't basically play others. And there are some quotes here like, I don't want to play on this clay surface, or grasses for golf players, which is reasonable, but still. And they're also mandatory events, so they cannot skip their tournaments. Finally, last week points count as last year. There is no recency concept in the points. I hope I don't lose anybody yet, but sum up, the system is a sum of the performance in the last 52 weeks rolling. And these points are used, as I mentioned, to enter the next week tournament, but also to give seed to the people. So what we would expect is that world number 1 and world number 2 don't challenge each other until the final. And so if we have a, let's say, bias ranking, you would keep better player out of a tournament that they would deserve to attend, and you would also make stronger player match each other sooner in the tournament. And we don't want that, so we can say that also as a fan, what I would like to see is that these features, first of all, but also some predictive power. So let's say I want to know who is the best player at the moment in every point in time. And I would expect that word number 1 has probability, like higher probability of beating word number 3 than word number 2, and so on and so forth. So giving some predictive power to the matches. OK, so let's go with some theory. It's not a lot of theory, but still. The model that will help us to address these challenges is called Bradley Terry, which is a probabilistic model for pair comparison, which are the matches. And in tennis, these are sparse. We don't see every single pair. We have a very sparse set. And the assumption is that the probability of one player to beat another player is based on a function of their abilities, which we don't know, which are theta I and theta j. It's logistic regression, after all. So the probability of player I beating player j is given by the logistic of the difference of their abilities. If somebody didn't see a logistic regression before, you take a real value and you map it into 0, 1, which we will interpret as a probability. So the example here, we have theta 1 and theta 2, and the difference is somewhere in between. You map it, and you get the probability of player 1 beating player 2 of 92%. Yeah, what we're interested in learning are their latent abilities, and this model will serve us also to model their abilities in different ways that given some assumptions. So let's start with what we need to build such a model, some data. Where the data come from? It's called this amazing GitHub repo by Jeff Saxman is the real hero of the story. It's a very well-maintained data set. Please go help him if you can, if you're interested to. I just focus on 2 years. Like his data set is from the beginning of time, basically. I'm also excluding like team events, national events that players most of the time don't really care about. So they not be so much informative. And also, I'm excluding players that have less than 10 matches in 2 years. And we are left with 200 players. OK, let's say we have a function to load the data from 2021 to today. We have 6,000 matches. If we check how the table is, something like that, we have tournament name, the date of the tournament, which is the same for every match. It's not the date of the match. The surface they played in. We have 3 surfaces, clay, hard, and grass. Who won, who lost, and the respective ranking. OK, this is, I swear, the last premise slide of what we need to know. I'm basically doing cross-validation because a single tournament will not be very indicative of what we do. I'm treating this as you would do with a time series validation. So I have training on 52 weeks and forecasting for the following tournament or following week. OK, so let's start from a baseline. Somebody yesterday mentioned baselines are important, so let's start from there. We have a ranking, as I mentioned. We cannot say that it has some predictive power, and so we will assume that the better ranking player will win the match. And let's do that in pandas. We first create a Boolean column, which is called best rank win. And if the winner rank is lower than the loser rank, then that's the case. We select only the test period, which, since we have 52 weeks of training, we'll discard the first year. We select the column, we take the mean, and it's not even 62%. And is it good? Maybe. I mean, it's not that far from a coin flip. And since it's a two-player match, then I don't know. But this is to be expected. There are a lot of upsets in tennis. You cannot expect that world number one wins every single match, right? Because that's never the case. And so there are a lot of upsets every week. OK, so how many people used PyMC or some Bayesian framework before? OK, less than expected. OK, very short summary about PyMC. It's a probability programming framework. It's based on a tensor library called PyTensor, which provides automatic differentiation and compilation. And PyMC provides all the distributions and all the sampling methods that one needs in these cases. So there are some PyMC developers that maybe will get angry at me. I hope not. OK, so how do you work with PyMC? You import a module, and then you build a model entering the context manager, which we alias as base model. So now we are starting to address all the issues that I mentioned, and this model will just address the fact that it can be a number game, and it's not opponent-based. So these are what we'll solve at the end of this slide. We enter the context, and then we assign an x and a y, which are the x to train and the target variable. And I'm using this mutable data object, which we'll see why in the future. And then you can slice this tensor as you would with NumPy arrays. So I'm selecting the first column of the x and the second column. And the x is the indexes of the players in a match. So we have player index 63 against player 47. And since in our table, player 1 was always winning, we have that y is always 1. And that's how it's built. Then we need some priors. So I'm creating two priors. One is for the mean of the ability, and we have one for every player. So you can see that it's a normal distribution, centered at 0, sigma 1. We don't have much information. And there is shape equal number of players. So we have one of these for every player. And then we have one single standard deviation, which is kind of hierarchical model direction. And then we multiply these together, and we get the single player ability. And then these two variables, one is PM deterministic. What does it mean? It means that in the sampling, the engine will keep track of this variable. And then, so you can imagine as player ability is a tensor of shape, the number of players. In each index, there is such player ability. And then when in the next line we slice with the index, we select that player ability, and we take the difference. And this is also a deterministic variable, but we don't care about the delta. So basically, I'm not tracking that. And finally, as we saw in the model, the delta between the abilities is the input to the logistic function, which we are tracking with a deterministic. And this probability is fed into a Bernoulli distribution. So what the intuition is, since the outputs are always 1, you would imagine that the model tried to push this probability as high as 1 as it can all the time. As large as it can, because then the output of the Bernoulli of the logistic will be as close as 1 as possible. OK, so this is how the model is built. And then we need to fit the model, right? So we don't have the dot fit as in scikit-learn. Thomas would say that there is another inference magic button. So again, we enter the context with the name we gave to the model. And then there is the dot sample function, which takes a bunch of parameters, which probably need a talk on its own. But you can decide which sampler to use and which are every parameter of the sampler and so on. How many chains and how many samples you want. You do that, and then you wait, right? That's like, OK. Sampling takes time. You can move it to GPU if you want. It takes time usually. So you feed the model, and then what you get is some posterior trace. Sorry, I didn't mention that. I'm saving the trace, which is not just the feed the model, but you also have some other information. So you take the trace, and it's a RViz object, which contains the posterior and the sample statistics, which are some statistics which give you an indication if the model converged well, if there were issues with the model, if anything went wrong, and so on. And then it's also to keep track of some of the data. What's in the posterior? So everything we tracked, so player ability, the means, and the probabilities are in the posterior. So this will be number of samples times number of chains for each variable. And to give you an example, these are the traces of the posterior of the top 10 players for a single sampling time, for a single fit. And it looks quite well normal distributed. And you can see there is a couple of players that are distant from the others, and then there is a lot of intersection between other players' ability. Cool. We need to predict. So for a lot of time, PyMC has been quite a pain in to predict on new data. Now it's become very simple. So if you remember, when we introduced the data was a mutable object. So what we just do is, OK, we enter the context again, and then we set data. So we set our x to the test data, and the y we don't care, because that's what our target. So it's empty array or something. And instead of sampling, we do sample posterior predict, which is the analogous of dot predict in scikit-learn. And we can also decide what variable to trace with var names. What's in here? It's RViz inference data object, contains some posterior predictive, which are the results, basically, and some data. And for each result, you have a distribution, which is cool. OK, nice. We backtest these, and it's half percent point above the baseline. So that's good enough. OK, fair. Everybody's laughing. But at least it has the two of the four problems that we wanted to address. OK, so let's go a slightly more complex model to address them. So I call this model ability by surface with decay, because I didn't have time to show like every single step. So I put them together. You enter a new context. It's called model. Again, you have the data, x and y. And x is basically your array. And the first column, second column are the indexes of the players. And then you have the index of the surface. And then you have sample weights, which is very similar to what we will do in a scikit-learn model. And it's a decay function. So the last week weight is 100%, 1 week ago, 99, and so on, decaying until 52 weeks ago, so that the model will give more importance to the most recent weeks. This block is exactly the same of the other model, so nothing new here. And now we are introducing the same shape, the same concept, but we have a surface factor for player, for surface. So it's a lot of more parameters now. And finally, we combine the differences between like what I'll call the core ability, which is the base delta, and the difference of the surface-specific ability. So basically, we are giving a bonus for a surface for each player, if they deserve to. Finally, we feed that into the logistic. We got the probability. OK, now how do we use the sample weight? Like PyMC doesn't have out-of-the-box way to do that. So basically, what the sampler does is let me pass this term, it's optimized for the log likelihood of the entire system. And so we create our custom log likelihood, and we can do that with PyMC potential. So we multiply element-wise the Bernoulli results times the weights. And now last week will count as ones, and previous week will count less and less and less. And then what the sampler will optimize is this error, which is error name there. We do the same, we feed the model, we check that everything converges well, no issues, blah, blah, blah. And then finally, we run the backtest, and it's 1.5 above baseline. Yay, everybody's happy, right? Cool. Still, like what I wanted to achieve is having a different system or a different way of looking at the problem. So yeah, that's basically what the model does. We'll see if we can improve that. Yeah, so ranking, how we can use that for ranking. So the main thing is now we have posteriors, so posterior distribution, so we can use that. I'm focusing here on a single week, but we can do that for every week of backtest. And comparing one of the actual ranking, which is the rank column, to what we will get if we rank with the median of the ability. So this is the core ability, the right column, and then we have the rank based on that. And it's kind of similar, the top 10 is kind of similar, it's shuffled in different ways. There are a couple of outliers, and then we can do that for every single surface. The outliers are still there, and like the main difference is Casper Ruud. Like he's number 4 in the world ranking, but like the model would say something else. And it's because his 2022 was amazing year, and 2023 is not going so well due to many reasons, but the model captures that very early. And so now if next week there is a tournament, we wouldn't place that as a seeded player, right? So that's what the premise was of the talk. Another way of comparing ranking is like over time. On the left, you can see the actual ranking of the top 4 player of the model. And you can see it's kind of static. Yeah, it's not very, I don't know, it doesn't update very soon. It's static, it's there. While on the right, it's the posterior ability, the core ability. And it looks like an actual process, maybe a Gaussian process or something. So yeah, it's way more dynamic. Yeah. Cool application, yay. Why Bayesian? There is the big debate. Bayesian, again, frequentist. I don't want any war anymore at all. But what is cool is that, again, we have posteriors, we have distribution. So what we can do is to use them. We can do all the prescriptive analysis and analytics with that. These are word number 1 against word number 3, and we take the probability of one beating the other on 2 surfaces. And, well, we have quite a substantial difference. Well, as you can see, the distribution is very wide, like from 10% to 90%. So not much indication. It's reasonable. It's word number 1 against word number 3. If we go with Djokovic, word number 2 with the model, and against Ruud, like we can see that like all the density is above 50%. So we are pretty sure that that will be the case in a match in both surfaces. Like, but Ruud is a clay specialist, so he has 5% more with respect to the hard court. So that's that. Okay, cool. It was a fun weekend, raining in Berlin. Where to go from here? So there are a lot of stuff that can be modeled in addition to that. Other factors, such as fatigue, you can include. Other priors. So as I said, there are a lot of upsets in tennis. So you could consider more robust priors, more robust outliers. For example, a student T distribution as a prior. Different model architecture. Hierarchical model. Like here I have a parameter not shared anywhere, but you can do that. A Gaussian processes. As we saw, like the ability looks like a process in a way. Extend the period of analysis, please, somebody. My laptop was burning all the time while sampling, and compare with other models. So Elo rating is another way of doing that. It's frequent. I don't know if there is a Bayesian version, but there is for sure a frequentist version that can do that. And other applications. So you can apply that. First, you can extend to draws and ties. So, for example, football and chess. And I also learned that you can extend to for LLMs prompts to evaluate them. Didn't know that, but apparently you can. And to conclude, I had a Bayesian joke, thought about it a long time, thought it was funny, but I told them to a few friends, and now I'm sure that it's not. Cool, that's it.